I can see Aguero has finally joined us.
Leo ako msituni.
Ako msituni. Naonekana asiye peke yake, bado wengine wanakuja. Okay, so there is one part of the previous slides, the typed ones that we didn't do. So maybe we can start with that, then we move back to the handwritten. I need to can you confirm that you can see my?
Yes, we can.
Okay, so I think we had done a lot of this stuff. So very first class, this is what we did, I think. Had we done this part about the unit vectors in the X, Y, and Z directions? I think we have done most of this. How to construct a unit vector. We can start from here. There are only 3 slides, so I will look at this quickly, then we can switch back to the handwritten ones. So here we will define a unit vector. So a unit vector is just a vector which has magnitude 1. So anytime we have a non-zero vector, we can construct a unit vector as follows. We divide the vector by its magnitude. If you divide the vector by its magnitude, you will get a unit vector in the same direction as the vector itself. So this small a is a unit vector in the same direction as a. So it's a unit vector or a vector of length 1 in the same direction as a. Okay, so we will be using these unit vectors frequently. The unit vectors that are in the same direction as the x-axis, the y-axis, and the z-axis. So the unit vector in the direction of the x-axis usually will be labeled I with a small hat on top. The one in the direction of the z-axis will be labeled as K with a small hat on top, and the one in the y direction will be labeled as J. So those are all unit vectors in those directions, and we shall be using them frequently. Now, if you have any vector in 3 dimensions, you can write it in terms of those unit vectors. So you simply pick the coordinates of that vector at the terminal point of the vector, and the first coordinate becomes the coefficient of the unit vector I. The second coordinate becomes the coefficient of the unit vector j, and the third coordinate becomes the coefficient of the unit vector k. So that the vector itself A, so this vector A will be written as the sum of these vector components. So now the length of the vector will simply be given by the sum of the squares of these coefficients, these A1, A2, and A3. You square them and add. Actually, this is wrong. This should be the square root of this. It should be the square root of this whole quantity here. We shall repeat this in the handwritten note, so not to worry, we shall correct that. So the magnitude is the square root of this quantity. So the magnitude is just the length of the vector. That's what it means. We'll close this, then I share the handwritten presentation. Some of the basics of vectors you already know. So a lot of this will just be to make sure we're on the same page, but some of it will not be entirely new to you. So here we'll talk about the dot or the scalar product. So we want to see how we can do some more operations on vectors. So we define the dot product of two vectors, A and B, and we denote it by A dot B. Define it as the product of the magnitudes of the two vectors, A and B, and the cosine of the angle between the two vectors. So once you have the two vectors, you simply need to find the magnitude of A, magnitude of B, and the cosine of the angle between the two. And when you multiply all those three quantities, you will get the dot product of the two vectors, A and B. So now the vectors are supposed to have bars on top, but I forgot to put the bars on top of this. So these A and B are vectors. There should be a bar, a straight line up above here. So in symbols, we will denote the dot product as, oh, there you go. So we have A dot B will simply be the magnitude of A multiplied by the magnitude of B and multiplied by the cosine of the angle between A and B. So these are the properties of a dot product. We may prove some of them, but may not prove some of them. So maybe before we proceed, we can make the following observation. If the angle is 90 degrees, if theta is 90 degrees so that the two vectors are perpendicular, then the cosine of 90 degrees is 0. So this dot product will just be equal to 0. So anytime the angle is 90 degrees, or when the two vectors are perpendicular, the dot product will be equal to 0. So another thing I'll mention is that the dot product of two vectors does not give you another vector, it gives you a number. So anytime you get the dot product of two vectors, you do not get another vector, you get a scalar. In our case, the scalar will be a real number. And you can see that because the magnitude of a vector is a number. So these two are numbers. The cosine is also a number. So the result is just a number. Keep that in mind very clearly. It will be useful. So we look at some properties of the dot product. The dot product is commutative. That's property number 1. So that's this property. It means the order in which you perform the dot product does not change the result. You can do it as A dot B or B dot A. Any of those will work. A second property is what we call the distributive property, so that a dot product is distributive over vector addition, so that A dot B plus C is equal to A dot B plus A dot C. So keep these properties in mind because you shall be using them. If you multiply the dot product of two vectors by a scalar on the outside, then you can multiply by one of the vectors first, then get the dot product, still get the same result. So these unit vectors in the direction of the x, y, and z axis have the following properties. I dot I and j dot j and k dot k will be equal to 1. And also I dot j. The reason for this is if you work out the angle between I and I is just 0, and the cosine of 0 is equal to 1. since the cosine of 0 is 1, if the magnitude of I is 1 and the magnitude of I again is 1. So if you multiply 1 times the cosine of 0, which is 1, you still get 1. That applies to all these three cases. Now, on the other hand, the three vectors are perpendicular to each other. The way they were set up, they are perpendicular to each other. Since they are perpendicular, the dot product will be 0, because the cosine of the 90 degrees is 0, and therefore this is what will happen if you get the dot product of I and j, or j and k, or I and k. These will all give you 0. It's 0 the number, not the vector. So I've made a mistake. There should be no bar up here. This bar should be removed. It's just 0 the number, because the dot product always gives you a number. So this bar 0 is wrong here. It should be the 0 the number. So the next property is if you have two vectors, A and B, and we write them in terms of is I, j, and k, then the dot product of the two vectors is simply A1, B1, A2, B2, plus A3, B3. We shall prove this later. And that means also A dot A, if you get the dot product of a vector with itself, it simply be the same as the squares of these coefficients of I, j, and k. So that would be A1 squared plus A2 squared plus A3 squared. So again, this is an important property. So there are two ways you can compute the dot product. One is the original formula, which requires you to just get the magnitude of the two vectors, multiply them, and multiply by the cosine of the angle between them. But we already know how that works with I, j, and k. So we can just write them out as in terms of I, j, and k, then proceed to get the dot product, because we know how the dot products of I with itself, j with itself, or I, j, and k with each other, we know how they behave from the previous this previous property. Since we know all this, we can get the dot product of A and B and simplify it to A1, B1 plus A2, B2 plus A3, B3. The same thing happens to the dot product of a vector with itself. You have A dot A will be equal to A1 squared plus A2 squared plus A3 squared. So also you will notice that the dot product is a square of the magnitude of A. So if you want the magnitude of A, it's the same as the square root of the dot product of A with itself. The next one says if theta is the angle between two non-zero vectors A and B, then we can obtain the cosine of theta as A dot B divided by the magnitude of A times the magnitude of B. This is obtained by just making the cosine of theta the subject of the formula for obtaining the dot product of two vectors. Again, we repeat here that if theta is 90 degrees, A dot B will definitely be 0. Again, I forgot, this bar should not be there. I don't know why I've put it here. This is 0, the number, not the vector. So there should be no bar up here. It would be a good idea to have a notebook where you make note down these changes. You see on page 2, the 0 should be just 0, the number. So it's good for you to note it down so that when you're reading this, you don't confuse this. And since now you know that the dot product of two vectors must be a number, you should realize that this is a mistake. This one simply says you can bring the scalars together and get the dot product. The next property says if you have two vectors A, no, that one is not complete. I think I didn't need that property, so I didn't finish it. So here is another topic, small topic, which we call the projection. So if we have two vectors, A and B, what we're looking for here is what we call the projection of B on A. So the projection of B on A, it will be defined as this. You get the magnitude of A multiplied by the magnitude of B multiplied by the cosine of theta divided by the magnitude of A. But you'll realize that this top part is just the dot product of A and B. So we get the dot product of A and B and divide that by the magnitude of A. This will give you the projection of B on A. We shall see how this works graphically in a minute. We are going to see the why this indeed is the case. So if you have two vectors, this is A vector and this is the other vector B. So the projection of B on A is simply obtained by dropping a perpendicular from the tip of B all the way to A, so that this is a right angle here. Now the length from this point O to this point is what we call the projection of B on A. So we just need to compute this length. So the projection of B on A will just be this length from O up to this point labeled T. So T is a point where you drop a perpendicular from the terminal point of the vector B down to the vector A. That gives you the projection. So we need to see how do we compute this length. Now, if you use Pythagoras theorem, the length of this hypotenuse is just the magnitude of B. So if I want this length is exactly the same as the magnitude of B multiplied by the cosine of theta. So I can multiply this by 1. The one that I pick is the magnitude of A divided by the magnitude of A. And so I can look at this OT as a vector. If I think of it as a vector, it's in the same direction as the vector A. So I can write OT as a multiple of a unit vector in the same direction as A. So if I have a small unit vector in the direction of A, OT would be given by the length of OT multiplied by the unit vector in the direction. So if I want to write OT as a vector, then I will get the length of OT and multiply that by a unit vector in the direction of A. So that's what we are describing here. The vector OT is given by the length of OT, which we obtained as this already, multiplied by a unit vector in the same direction as A. But the unit vector in the same direction as A is simply the same as the vector A itself divided by the magnitude of A, capital A. And the magnitude of OT also can be taken as the magnitude of this vector. But since we know that the magnitude of A is 1, we still end up with the same thing we had earlier. Magnitude of B multiplied by cosine of theta. So we shall write this formally now. All these things we have been putting up there. So projection, oh, this is a repeated slide. Okay, I think that's it. So the thing to remember here is this formula, the projection of B on A. So focus on this notation. Projection of B on A requires that you have A as a subscript here, and then the vector that is being projected on A appears here. And the formula will simply be the magnitude of A multiplied by the magnitude of B times the cosine of the angle between the two vectors, and all this is divided by the magnitude of A, which again can be simplified to A dot B divided by the magnitude of A. So remember, the projection is also just a number. It is not a vector, because all we are interested in is this length from O to T. We are not interested in the vector, it's just the length. So the projection of B on A is a number. And you can tell that from the formula. The dot product always gives you a number. So we'll look at some examples that will take us through some of the properties that we have done. So here is an example. It says if A is equal to A1I plus A2J plus A3K, and B is equal to B1I plus B2J plus B3K, there are two vectors, then we need to show that A dot B will be given by this expression, A1 B1 plus A2 B2 plus A3 B3. So the way to do that is simply do a direct computation. Just do the substitution for A as this, and the substitution for B as B1I, B2J, and B3K. So when you expand this, you can take, you're getting the dot product. You can use a distributive property of the dot product. So you can get a dot product of just this first vector A1I with the whole of the vector B, and do the same for the next one, the dot product of A2J and the whole of B, and the dot product of A3K and the whole of B. We do that in sequence, and when we work it out, this is what we have. A dot B will be A1 B1 I dot I, and so on, all the way up to A3 B3 K dot K. So that's easy to obtain. Like for the first one, you will have A1 B1 and I dotted with I, the dot product of I with itself. Then you have A1 and B2 with the dot product of I and J, and the third one is A1 and B3 with the dot product of I and K. You do the same for the others, then you write out everything here. So, but you need to remember a few things. We know that this I dot J, I dot K, J dot I, and J dot K, K dot J, and also K dot I will all be equal to 0 because those vectors are perpendicular. So the only terms that will survive here will be A1 B1 I dot I, and A2 B2 I dot I, and A3 B3 K dot K. But we know that K dot K is equal to 1, so we can replace each of those by 1, and we are left with A1 B1 plus A2 B2 plus A3 B3. So the relationships we have used are also here. These ones we know to be true, so we can use them up here and simplify our expression to this. So that proves that A dot B is the same as A1 B1 plus A2 B2 plus A3 B3. So here is another example. It says that in any triangle ABC with the usual notation, prove that B squared is equal to A squared plus C squared minus 2, usually write AC, but here is CA, 2CA cos B. So this is a cosine rule. It's the one I think you're familiar with it, but we want to prove it using vectors now. So to prove it using vectors, first draw the diagram. So a triangle works like this. There are two ways to have a triangle when you have vectors. Either the resultant of the three vectors will be 0, or one of the vectors will be equal to a sum of the other two. Any of those two conditions will give you a triangle. So we have picked this situation where A plus B plus C is equal to 0. So we can make B, if we put A and C on one side, we'll have minus B will be equal to C plus A. So get the dot product of each side with itself. Because they're equal, the equality would still be retained, because B and C plus A are the same. So if I get dot product of B minus B and B, and the dot product of C plus A with itself, my equality is not lost. I still have the equality. So now we can work out both sides. On this other side, you'll have B dot B is the same as the magnitude of B squared, and C dot C is again the same as the magnitude of C squared. A dot A again is the same as the magnitude of A squared. And these two can be combined to have, because C dot A is the same as A dot C. So we can replace C dot A with A dot C. And then we have two of these. So we can just write them as 2 A dot C. Now, the dot product of A and C, in this case, remember A is this and C is this. Now, because of the direction that this C is facing, the angle between A and C is obtained by bringing the tail end of C and putting it at the you could bring it and put it here. So it will be a cosine of the angle which is pi minus this angle. No, actually it will be exactly this angle, but pi minus B still works. B is this angle. B is this angle here. So if you take this vector and put the tail end at the terminal end of A, then it will be a vector running like this, so that the angle that this C makes with A will be this angle, which is the same as that angle, because the line that I would have drawn here will be parallel to this one. So this angle and that angle will be equal. So the angle between A and C is just this angle B. So we can replace the angle as B, and we have B squared is equal to C squared plus A squared plus 2AC multiplied by the cosine of B. Now, we made some statements before that we take the magnitude of A to be this small a, the magnitude of the vector B to be just this B, and the magnitude of the vector C to be equal to this C. Now, this is the notation you are used to from your trigonometry, right from high school. That's why I have used it, because it's familiar. So this proves the cosine rule using vectors. B squared is equal to C squared plus A squared plus 2AC times the cosine of the angle between the vectors A and C, which is just B. So we look at another example. We need to show that the magnitude of this vector written in this form is given as magnitude of A is equal to the square root of A1 squared plus A2 squared plus A3 squared. So let's draw the vector first. If the vector is this OP with coordinates A1, A2, and A3, so we have this point P as the terminal point of the vector A, and it has coordinates A1, A2, and A3. A1 simply means you have to move A1, the distance A1 in the X direction. You move a distance A2 in the Y direction, and a distance A3 in the Z direction. That's how we get these coordinates. for this point. Now we can use, because this is a cube, it has a lot of right angles. So OP, this OPQ is a right angled triangle. So we can say OP squared, this is the hypotenuse, will be equal to the sum of the two shorter sides. One of them is this OQ squared. Then we have QP. So we put QP squared here. This is just Pythagoras theorem. We also can use that on this other triangle, OQR. Use it on OQR, then you have OQ squared is the same as OR squared plus RQ squared. So this OR plus OR squared plus RQ squared should be the same as OQ squared. And the same idea is also on OP. Now, OP, we can replace, you see this OQ, we can replace it with this term. So we replace this OQ squared with the whole of this. Someone is trying to join. I'll admit them. So when we replace this term for OQ, we end up with this expression that OP squared is OR squared plus RQ squared plus QP squared. But OR is just this distance A1, so I can write it as A1 squared. RQ is this distance, but it's the same as the distance from O to S, which is A2. So I can write it as A2 squared. And then QP is this distance, but QP is exactly the same distance as this distance from O to the top of this cube. And that is the distance A3. So I can replace QP by A3, and I have OP squared will be equal to, so OP is the distance from O to P, and that is the magnitude of my vector A. And OP squared will be A1 squared plus A2 squared plus A3 squared. So if I want to get OP, I just get the square root of this. So that means the magnitude of A, which is now OP, is just the square root of A1 squared plus A2 squared plus A3 squared. So are there any questions? So sometimes you have vectors whose initial point is not at the origin, and then you need to work out the position vector for such a vector. So here we consider a vector which has an initial point P and a terminal point Q. Now the position vector for P, the position vector for P is just x1, y1, z1, and the position vector for the second vector, I mean the terminal point of P, of the vector. So the position vector for the initial point is this, and the position vector for the terminal point is this. That is what we have, and that is drawn here on the diagram. Now I want this vector with the initial point P and terminal point Q. To get it, I can see that I can call that vector PQ. So R1 plus the vector Q will be equal to this vector R2. So that PQ is the same as R2 minus R1. And when I get R2 minus R1, it's the same as X2 minus X1I plus Y2 minus Y1J plus Z2 minus Z1K. So now I have my vector PQ, the vector with terminal point Q and initial point P. I can now write it as X2 minus X1I plus Y2 minus Y1J plus Z2 minus Z1K. I can also get the magnitude of this vector, so that the magnitude will simply be x2 minus x1 squared, y2 minus y1 squared, plus z2 minus z1 squared. So so here's an example where we are given another example, we have 4 vectors. Then we are asked to find the numbers. This bar should not be on the A. It should just be a small a with no bar. It's a number, not a vector. So we want to find 3 numbers, A, B, and C, such that R4 will be equal to AR1 plus BR2 plus CR3. So the best way is simply to find the values of AR1, BR2, and R3, and then equate to R4 and compare the coefficients. So that's what we have done here. This is A multiplied by R1, B multiplied by R2, and C multiplied by R3. So we pick all the like terms together. All the terms containing the vector I hat, the unit vector in the x direction, are put together, and the first coefficient is 2a. You can pick the second coefficient as b, and the third one as minus 2c, because there's a c out here. So minus 2c. That's what we put as a coefficient of I. We do the same thing for a similar thing for the j and also for k. So now we have the vector R4. And we know what the first component of R4 is 3, right? So we can equate this to 3. The second component of R4 is 2, so we can equate this quantity to 2. And the third component of R4 is 5, so I can equate this component to 5. That gives me a system of linear equations here. Now, the solution for this is A is equal to -2, B is equal to 1, and C is equal to -3. I have not taught you how to solve this, but for now you can take this as the truth. We shall learn how to, we will learn how to solve this. So we have found the numbers A, B, and C, where A will be -2, B will be 1, and C will be -3. So in your own time, you can check and confirm if indeed R4 is equal to this expression on the right-hand side. So R4 was already given up here, in case you're wondering where I'm getting 3, 2, and 5. R4 was given from the problem. So 3, 2, and 5 actually came from the statement of a problem. So this one you can solve. And you get A is -2, B is 1, and C is -3. I think we can start from there tomorrow. We have just about 6 minutes to go. So we can start from here. Oh, today is 2 hours, right?
1 hour.
Tomorrow is 2 hours. Yeah.
No.
I almost told one of your hours, but you didn't let me get away with it. So what do you suggest? We continue?
We meet tomorrow.
We meet tomorrow. You want to go
Yes,
and
sir.
take the evening tea?
Yeah.
We have another lecture.
So we stop there. I will share the video.
Yes.
Is that okay?
Okay, sir.
And the notes.
Unless you have questions. If you have some questions, you can ask in the remaining time. But if you have to go, you can leave. Hakuna swali?